Hi, my name is Silvana Aristizabal, and this is my lab report for Lab 3 on black holes and orbits. Here's the table of contents of what we're going through in this presentation. Firstly, the introduction. The overall purpose of this assignment is to simulate and analyze the motion of celestial bodies to estimate the mass of a black hole and explore gravitational orbits. For part 1, we will be estimating the black hole's mass based on the star's motion, and for part 2, we will calculate gravitational forces acting on the moon and spaceship, and then adjust the spaceship's initial velocity to ensure it orbits both bodies without crashing. We will achieve this using one main tool, GlowScript, for building the two computational models. All of this helps us gain a deeper understanding of the bigger picture behind Newton's second law of motion, gravitational force, and net force. So let's explore more about these fundamental principles. So the momentum principle states that the net force acting on an object is equal to the rate of change of its momentum over time. In other words, when a force is applied to an object, it changes its momentum, which is the product of its mass and velocity. We can see here how by deriving from the momentum principle, we can obtain the velocity update formula. This formula allows us to determine the object's velocity at each time step when dealing with a non-constant force. Once we have the updated velocity, we can use it in the position update formula to predict the object's future position over time. For the net force is acting on an object. The net force acting on an object is the vector sum of all its forces acting upon it. It can be broken down into perpendicular and parallel component. The perpendicular component points towards the center of motion, and in circular motion, it acts as a centripetal force maintaining the orbit. The parallel component points towards the direction of motion and is responsible for changing the object's speed. The law of gravitation states that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. For part 1, we will use it to determine the mass of the black hole by analyzing the force acting on the star, and for part 2, we will use it to calculate the gravitational interactions between the spaceship, planet, and moon affecting the orbit. Now, let's take a look at the models we've constructed. For part 1, the system is the star plus the black hole and the surroundings with everything else. So for the code, what we first had to do was input the seed that was unique to everyone. Then we had to calculate the initial and final velocity, then the initial and final momentum, then the change in velocity and momentum. Here we calculated the net force, which is equal to the rate of change of momentum. Then here we calculated the components of net force, the parallel component and the perpendicular component. And lastly, we calculated the mass of the black hole, basically solving for m in the gravitational force formula. Then we adjusted the arrows so that they pointed in the direction of the force they were labeled as. So our results here indicate that the mass of the black hole was 1.580054 times 10 to the 36 power kilograms. We can also calculate the net force and then divide it into the perpendicular and parallel components. Now let's take a look at part 2, where the system is the planet plus the moon plus the spaceship, and then the surroundings is everything else. Now for the code, we first had to calculate the gravitational force on the moon by the planet, then the gravitational force on the moon by the spaceship, then the net force on the moon, then the gravitational force on the spaceship by the planet, the gravitational force on the spaceship by the moon was calculated after that, and lastly, we calculated the net force on the spaceship. With all of this, we were able to use the velocity update formula and the position update formula to update position for the moon and ship trajectory here. So for our code, we needed to try different initial velocities to see which one led to the spaceship and the moon orbits not crashing. For my specific code, I got that the initial velocity for no crash would be 24,250 meters per second, both in the x and y direction. So now let's take a closer look at the possible sources of error in our experiment and how they may have affected our results. So computational errors like rounding errors and time step approximation errors could have affected our calculations, while neglecting other forces and treating the star, planet, and moon as point masses could have affected the accuracy of our model. So to reflect on the lab, let's answer these questions. Think about what rate of change of momentum means and what net force means in terms of things you can observe and measure. So according to Newton's second law of motion, force is directly responsible for changes in an object's momentum. Thus, dp dt, which is the rate of change of momentum, is equal to the total force acting on an object, thus the net force. The perpendicular component of net force alters the direction of its momentum. Thus, we can see a change in direction in terms of position, and the parallel component of net force alters the magnitude of momentum. Thus, we can see a speed increase, decrease, or how it stays constant. If you wanted to predict the motion of the entire system, what would you need to include in your computational model? Would there be any dominant interactions, or would they all contribute more or less equally? So we would need to include the gravitational forces between all objects, the initial positions and velocities, the update velocity and position with Newton's second law. then some interactions will dominate. For instance, the interaction between the black hole and the star will be more dominant than the interaction between the planet and the star because of their masses. Thank you.